Hello everyone. In this presentation, we are going to look at how Jupyter Notebooks can be used for power electronics education. In particular, we will see how circuit simulation can be integrated with Jupyter Notebooks for the purpose of power electronics teaching. Here is the outline of this presentation. First, we will look at why we need circuit simulation at all for this purpose. Next, we will look at a circuit simulator called GSEIM, the one that we are going to use in this work. We will look at the block diagram of GSEIM. We will also look at the circuit file, the format of the circuit file or netlist that is required to run GSEIM. We are then going to look at the interaction between GSEIM and Jupyter Notebooks, the mechanism that is involved for this interaction to happen. Then we will look at this folder called Jupyter GSEIM. What are the various files in that folder, what each one of them is doing, and so on. And then finally, we will put it all together and look at a GSEIM based notebook. Just go through all aspects of that notebook. Okay, so to begin with, let us discuss why we need circuit simulation at all for the purpose of Jupyter Notebooks to be used in power electronics. We will illustrate this through two examples. Here is the first example. Let's read out the problem statement. The current and voltage waveforms for an IGBT during the turn-off transition are given. And these waveforms are characterized by various quantities like I1 here, I2 here, V1 here. These are the current and voltage levels. And delta T1, delta T2 are the time intervals. And some of these values are given. I1 is given to be 20 amperes, I2 is 10 amperes, delta T1 is 2 microseconds, delta T2 is 4 microseconds. So all of these are given. In addition, we are told that the energy dissipation in the switch during the turn-off process is some 13.3 millijoules. And given all of that, we are supposed to find V1, this level here. Let's suppose that there is a student who has looked at this problem and has solved it through much hard work and has got some value for V1. Now he or she wants to verify whether this value is correct. So the idea now is to provide the student with a Jupyter notebook which will allow him to do that verification. Now the question is whether we need a circuit simulator for this purpose, and the answer is clearly no, because this problem is too simple. What do we need to do? We just need to write a Python shell which will construct arrays for the voltage and current, and this we can do with NumPy, and then use NumPy again to compute the power as a function of time, which is just V times I, and then the energy, which is the integral of the power with respect to time. And all of these can be very easily accomplished using NumPy. Let us consider this next example now, which is more complicated than the earlier one. So the problem statement says that the periodic current Is through the switch S for a buck boost converter is given below. So that is the current that we're talking about, and here is the waveform for that current. This interval in which the switch is conducting is 20 microseconds. The interval in which the switch is not conducting is 30 microseconds, and also this peak switch current value is given to be 9 amperes. Apart from that, we are told that the output capacitor is sufficiently large to ensure a ripple-free output voltage. The source voltage value is given to be 50 volts. The inductance is given to be 1 millihenry, and we are asked to determine the load resistance R and the output voltage and the average value of the inductor current. What do we want our notebook to do in this case? Let us see. So the user is going to enter some value of the resistance R, and then we have all the parameters of the circuit. With that input, we should be able to calculate all the currents, the source current, the inductor current, the capacitor current, and so on, and also the output voltage. And we want to calculate not only the steady state average values, but the actual waveforms, because those have much more information, and that is something that we can show the user so that he or she can verify whether their current waveform, the switch current waveform, is indeed like what we have given. And that is too difficult to do, if at all it is possible. And that is the reason we really need to use circuit simulation. If the question was, let's say, calculate only the average value of the output voltage, then we could have used an analytical formula, and then the user could have verified whether the VO that they have matches with the actual analytically computed value. But here we are actually trying to show all the waveforms, and for that we do need a circuit simulator. So in such cases, circuit simulation is very convenient, and we will see many examples of this. We are going to use a simulator called GSEIM. GSEIM stands for General Purpose Simulator with Explicit and Implicit Methods. It's an open source package, and it's available at GitHub. You can take a look. As the name suggests, GSEIM allows implicit as well as explicit methods. And let's talk a little bit about numerical methods. Implicit methods such as backward Euler, trapezoidal are very commonly used in circuit simulation, and PSIM and SPICE are some of the circuit simulators, also PSCAD, which use these methods. And implicit methods are popular because they allow relatively large time steps, which means we have to take fewer time steps to cover a given interval. That makes the simulation faster. There are also explicit methods such as Runge-Kutta or Runge-Kutta, Fehlberg, 4, 5, and so on. Now these explicit methods are faster, but there is a big if over there. They are faster if the time constants in the system are not too small. One of the packages that use explicit methods is MATLAB Simulink. In power electronic circuits, switches which are in the on state, that means switches which are conducting, give rise to small time constants because they are represented by very small resistances, and that makes explicit methods difficult to use. That really rules out explicit methods for power electronic circuits, and implicit methods really are then the only choice because they are far more efficient than explicit methods. There is one different approach that is used in the simulator called Plex, and what they do is they avoid the small time constants which arise because of conducting switches, and they do that by treating each switch as a perfect short circuit or a perfect open circuit, and this leads to a linear problem for each switch configuration, and that allows much faster simulation, because each linear problem basically means you have to solve Ax equal to B, and you can just compute A inverse once for a particular switch configuration, and you don't need to repeat that calculation again, and therefore this kind of approach is much faster. Of course, it's not valid in all simulations that people may want to do, but for several power electronic circuits this is a very fast approach. currently Plex functionality is being incorporated in GSEIM. Now in the notebooks that we are going to describe, we will use GSEIM with implicit methods only, and usually backward Euler. Apart from transient simulation, GSEIM allows something called steady state waveform or SSW computation, and let us see what this means and why it is very useful in preparing notebooks for power electronics education. This SSW feature is particularly useful for simulating circuits in which we are only interested in the steady state voltages and currents, and not really in how the circuit attained that state. So let's illustrate this through an example. Here is a boost converter, and the switching frequency is 25 kilohertz. So one time period is 40 microseconds. And in these situations, we typically are only interested in that steady state 40 microseconds of data, whether that is the switch current or it's the output voltage or the capacitor current or the diode current or whatever. Now if you perform transient simulation, let us say starting with some initial conditions, for simplicity say 0 volts for the capacitor and 0 amperes for the inductor. Suppose you start your transient simulation with these conditions, then we get something like this, the result on the left. That is the switch current as a function of time, and we see that it takes at least about 10 milliseconds for the circuit to reach steady state. What we are really interested in is this plot on the right hand side, that is IS in the steady state, and just 40 microseconds of data, right? Now if we compare this 40 microseconds with this 10 milliseconds, obviously the transient simulation involves a lot more work, lot more time. Now in this particular case, the circuit is small and it may not really matter, but if the circuit is larger, then the CPU time that it takes for transient simulation can be substantial. Apart from that, there is another issue with the transient simulation approach. As far as our purpose is concerned. So what do we really want? We want the user to play around with the circuit parameters such as the inductance or the capacitance values or the resistance, and look at the steady state output quantities, switch current and capacitor current and so on. Now if you change these values, we don't know whether the new steady state is going to be attained in 10 milliseconds, 15 milliseconds, 50 milliseconds. So that is an unknown. So that is something we don't know beforehand, and then that becomes a trial and error scenario, which is quite painful, and it's definitely not suitable for the notebooks that we are trying to prepare. Let's talk a little bit about the GSEIM package. It has a GUI which allows schematic capture, so one can bring in components, edit their parameter values, do wiring and so on. It also has a plotting interface, and that allows the user to see the quantities of interest. Here is the block diagram of the GSEIM circuit simulator. There is the schematic entry code written in Python. In fact, this is adapted from the GNU Radio package that interacts with the element library of GSEIM, and it produces a high-level netlist, and there is some parsing and parameter computation and so on. That also happens in Python, and after that a low-level netlist or circuit file is generated. Now this circuit file serves as the input to the engine or the C++ solver, and the solver works on the netlist and produces the output files that the user has requested. In preparing our notebooks, we are actually not going to use some of these blocks. So the schematic capture part we are not going to use. We are also not going to use the plotting program. We are going to use the C++ solver along with the element library, this block here, and the output files that the solver generates. Once we have the output files, those have all the data that we want, and we will use that data to compute, let's say, average values, RMS values, and so on. And the netlist or the circuit file that is shown here as low-level netlist is something that we're going to prepare manually using a text editor. And the question, of course, is why are we not using that circuit file or netlist generated by the GSEIM GUI? So let us see the reason behind that. What we see here is the circuit diagram as entered in the schematic capture GUI of GSEIM, and on the right hand side we see the corresponding netlist or circuit file. And as we see, the circuit section is enclosed between these two statements, begin circuit and end circuit, and there are some statements which correspond to the elements in the circuit. Let's look at for example the statement that corresponds to this resistor, 50 ohm resistor here, and that statement is right here. So it's an electrical element which has got name equal to R$1. Now this name is assigned by the GUI, it is not assigned by the user. Its type is R. Its P node is N0_3. This is also assigned by the GUI. N is 0, 0 is the reference node, and then there is this R equal to 50. As we have seen, the node names and element names are auto-generated by the GUI, and it is difficult to relate those with the circuit diagram. And the circuit diagram in fact does not show the node names, and therefore we don't know where this N0_3 is in the circuit. Instead, for the purpose of preparing notebooks, what we're going to do is to manually prepare the circuit file, which would look something like this, using a text editor like Vim or Emacs or gedit or Notepad, and then use that as an input to the C++ GSEIM solver. Here is an example of a manually prepared netlist or circuit file. On the left we have a circuit which we are going to show to the user when we prepare the notebook, and on the right we have the corresponding circuit file. And as we see, this circuit file is far more readable than the one that we saw, which was auto generated in the last slide. For example, this first statement says that there is an electrical element whose name is Vs. Now this Vs is a name given by us. We could have called it Vs1 and so on. And then there is the type equal to VSRC DC. This type is the name of that element in the library, which we will see a little later. And this particular element VSRC DC has two nodes, P and N. We have assigned A to node P, that is A. This is our Vs, and 0, which is the same as this ground here, to node N of Vs, and its value is 5 volts. Similarly, there is this inductor whose name is L, whose P node is A, N node is B, like that, and whose inductance is 200 U. 200 U is 200 microhenry. Also, there is a non-electrical element in this circuit, and that is denoted by this statement starting with X element. That non-electrical element is the clock which is driving this switch, not shown in the circuit, and it has its own parameters. D is the duty cycle, F hertz is the frequency in hertz, and there are some other parameters. One more important aspect that we should comment on is the so-called output variables, which are denoted by this outvar statement. In our circuit, we have defined 6 of these, and let's take the first one. It says IL, which is a name given by us. We could have called it IL1, for example. IL equal to I of L. Now this L here is the inductor, the name given to that inductor, and that is right here, name equal to L, right? So what this statement means is that we're going to call the current of the inductor by the name IL. Now if there are two inductors in the circuit, for example, and we have named those, let's say L1 and L2, we could have defined two output variables, IL1 to be I of L1 and IL2 to be I of L2. So there is a lot of flexibility in defining these output variables, and it all depends on what we want to see in the plots once the circuit simulator is executed. Apart from the circuit section or the netlist, the GSEIM circuit file also involves solve blocks. Here is an example. The solve block is always enclosed between the statements begin solve and end solve, and essentially it tells the simulator what it should do with this circuit. Now in this case, we have specified solve type equal to SSW. That means the simulator is going to perform steady state waveform analysis on this circuit. A solve block also contains several other important statements. For example, here is a statement that tells the simulator which method to use, in this case backward Euler. What are the tolerance parameters to use, and since it's an SSW simulation, what is the steady state waveform frequency, that is 25 kilohertz, and how many periods we want to see, that is 2 here. Apart from that, a very important aspect from our notebook perspective is this output block here, which is enclosed between the begin output and end output statements. Within the output block, there is a statement called file name, and that is the name of the file that we want to specify for the output file. In this case, it's a boost converter, and we expect it to be in the continuous conduction mode. So we have called this boost ccm1.dat. The other important specification is which variables this file should store, and we see here we are storing IL, IS and so on, and in fact these names come from our previous slide from the circuit block, and these are the output variables that we have already defined in the circuit block. So any of these names has to be in the output variables that we have defined in the circuit block. Now when the circuit file gets executed by the C++ solver, this output file will be created, and it will have all of these variables stored inside. The first column is always the time. The second column would be then IL, the inductor current. The third column would be IS, the switch current, and so on. Now that we are familiar with the GSEIM circuit file, we can look at how we can have GSEIM interact with a Jupyter notebook. And as an example, let us consider this problem. The problem statement is the boost converter in the figure is operating at the boundary between continuous mode and discontinuous mode. Certain values are given. The source voltage is 10 volts. The output voltage we want is 20 volts. The capacitance is given to be 200 microfarads. The inductance is given to be 62.5 microhenry. And the switching frequency is 10 kilohertz. For these conditions, we want the student or the user to find the load resistance value and determine the RMS value of the capacitor current. So we are going to give a notebook to the user and expect the user to enter the value that they have found for R, and with that value we are going to run GSEIM on a suitably prepared circuit file and compute all the waveforms that the user would like to see. And then the user will check whether the output voltage is indeed 20 volts. If not, then obviously there is some mistake in the calculation of R, and then the user would go back and calculate it again and enter the revised value in the notebook. That is basically the idea. So in short, as we mentioned, we want to enable the user to change the value of R. How do we do that? We prepare a circuit file, GSEIM circuit file called Bose CCM7 original.in, and in that file we include a statement like this: electrical element name equal to R, type equal to R, P equal to C, N equal to 0. So the resistor is between C and 0, the ground. And instead of saying R equal to 10 ohms or 15 ohms, we say R equal to some variable name like $R. Now what we do is use this code here to essentially replace that $R with the value that the user has in mind. Let us look at this Python code. The first statement is the definition of this string s_r, and this is just our name. Since it's a string, we have made it start with s, and that string is assigned the value 20. Now this 20 is basically going to translate to 20 ohms for the resistor, and it's going to be changed by the user. Then we open the original file, this file here, for reading. We open a new file, this file here, for writing, and for each line in the input file we look for the string $R, and of course we're going to find this particular statement, and we're going to replace that with the string that the user has specified. So that means it is 20. So this $R is now going to be replaced with 20, and the new statement will then say E element name equal to R, etc., etc., R equal to 20. So we write that line to the output file, and then of course we close the input file as well as the output file. It's as simple as that. Now on this revised circuit file, this file here, we run the GSEIM circuit simulator, and that will produce the output file that we have requested in the original circuit file here. Alright, so just to summarize, how do we create a new notebook? A GSEIM circuit file for the concerned circuit is written first. In this file we assign variable names to parameters rather than fixed values. For example, we say L equal to $L, some variable name, instead of L equal to 2e minus 3, instead of saying 2 millihenry, or VDC equal to some variable name $VDC, instead of saying, say, VDC equal to 50. Next, we create Python cells for the following. First thing we want to do is to replace $L etc. with their desired values, typically the values that the user would enter. This we have already seen in the last slide. Then create a cell which will run the GSEIM circuit simulator on the revised circuit file, and then create additional cells as required, for example to compute average or RMS values, or perform Fourier analysis and show the spectrum, and so on. In addition, we would also like to show some plots, for example what the current looks like in the steady state for an inductor or a capacitor, what is the output voltage, and so on. Next, let us see how we can use these notebooks. Let's say you are teaching a course in power electronics and you want to assign some homework. You have just taught some new concept, for example a boost converter or a buck converter, and you want the students to understand the continuous discontinuous conduction. In such a case, we can make up a notebook, and the problem statement then can be, for example, compute L, the inductance for which the converter operates at the CCM DCM boundary, and we share a notebook with them and ask the students to verify their results using the notebook. Another application, let's say you are a teacher and you have covered buck converter, boost converter, and so on, and you want to assign a problem based on these circuits in the exam. So you have made up a problem, you have worked out the solution, and you want to quickly check whether your solution is correct before the problem is actually assigned for the exam. For that, again, you can use these notebooks. Third, a picture is worth 1,000 words. That means if we show a plot in a classroom setting, that carries far more information than writing, let's say, 5 equations on the board. So after covering a specific circuit in class, the teacher can show plots which are related to that circuit, for example steady state capacitor voltage, steady state diode current, and so on. Furthermore, the teacher can change circuit parameters such as the load resistance or inductance value, and immediately show, with the help of the plots which the notebooks generate, the effect of that change of parameters on the circuit behavior. Let us now look at the files that we get when we download the Jupyter GSEIM zip file. Run gsim.exe, that's the GSEIM executable on Windows, and on Linux it is called run GSEIM without the .exe extension. Then we have the notebook files which have extension .ipynb. Then we have the circuit files which have extension .in, and they would generally have _ORIG for original also in their names. We have the .png files which are images which we are going to show in our notebooks, typically circuit diagrams. Then we have some files related to the element library, and all of these files are in a folder called GSEIM aux for auxiliary. There are 4 folders here: EBE, which is the electrical basic elements; XBE, the non-electrical basic elements; EBE doc, the electrical element documentation; XBE doc, the non-electrical element documentation. So let us look at some of these files. Okay, so here is our GSEIM auxiliary folder, and within that folder we see that there are these subdirectories: EBE, XBE, EBE doc, XBE doc. Let us go to the EBE folder and let us look at the register template, that is r.ebe. Alright, so here we have the first line EBE name equal to r. That means this element has name r, and that shows up as the type in our circuit file. Then there are various other things. The ones which are relevant are real parameters, and the most relevant real parameter of course is the resistance value, which is called r here. Its default value is 1. We also should see the output parameters. These are the output variables which are available to us. They are I, the current, V, the voltage across the resistor, and PWR, the power that the resistor consumes. In the same file, we also describe how this element behaves, or what is the equation that it satisfies. And in that sense, these element templates are completely decoupled from the C++ GSEIM solver. So here is the relevant statement. These two functions, nf1 and nf2, are the current specifications. So what is the current entering the P node of this device? What is the current entering the N node of the device? The current entering the P node is given by G, which is the conductance, times Vp minus Vn, and Vp and Vn are defined here. Vp is the node voltage at node P, Vn is the node voltage at node N. And corresponding to these functions, we also need to provide the Jacobian or derivative values, and that is done in these 4 statements here. There are several other blocks and statements in this template, but we will not go through all of that. The interested persons should go to the GitHub site, the GSEIM GitHub site, and there is a detailed manual of how these templates work. Alright, so let's look at some of the documents. So we change the directory to EBE doc, and here we find many PDF files, and these PDF files always start with BE for basic element and the element name .pdf. So for example, our resistor would be described in this particular file. Alright, so let's look at this file here. That's a PDF file. Its title is the name of the element, and it reproduces some of the statements which are in the r.ebe template, and it also informs us what are the real parameters, what are the output parameters, and so on. And then there is a brief description. So r.ebe is a resistor connected between nodes P and N. Nodes are here, nodes P and N. The resistance value is given by the product of the real parameters R and K scale. Normally we just use K scale equal to 1, but sometimes there are situations where we want to change several resistance values by a common factor, and that is why this provision is made. And the branch current and branch voltage are made available as output variables I and V respectively. So that is this statement here. So there are these PDF files for the other elements as well, and whenever the user has some doubts about this element syntax, these are the PDF files to refer to. Okay, so we will now go through a sample notebook, Boost CCM 7.ipynb, and see how all of these Python cells within that notebook are working. The problem statement is the boost converter given below is operating at the boundary between continuous mode and discontinuous mode. with Vs equal to 10 volts, the source voltage, Vo equal to 20 volts, that's the output voltage, capacitance equal to 200 microfarads, inductance equal to 62.5 microhenries, and a switching frequency of 10 kilohertz. And the reader, the user, is asked to find the resistance value for these conditions, and then also determine the RMS value of the capacitor current. Let us now look at the files which are relevant to our Boost CCM 7 notebook, and all of these files are located in our Jupyter GSEIM folder. So here are the files. There is of course the notebook file, then there is an image file which is the circuit diagram for the boost converter. Then there is this circuit file, the original circuit file, which is going to be used by the GSEIM solver. Alright, so let's launch Jupyter Notebook from this directory. That opens the browser, and here is our notebook. So we double click on that, and then the notebook opens. Here is our problem statement that we have already seen, and this cell here is used to display the circuit diagram, and we see the file name that we just came across. That is the image file. So if I do shift and enter, the circuit diagram shows up. The next cell is used to display this circuit file, boost CCM 7 underscore ORIG for original. So when we execute this cell, that is what we get. And notice here that we don't have parameter values. For example, the VDC, the DC voltage of the source, is specified not as a value like 10 or 20, but as a variable name. And similarly for the inductance, we don't have 10 millihenry or whatever, but $L, and so on. Notice also that we have our output variables defined here. For example, we have defined the current through the inductor as IL. We have discussed this before. This circuit block ends with this line, end circuit, and then the solve block starts with begin solve, and this particular solve block is of type steady state waveform, and all of this we have discussed before, so let's skip that. Alright, so the next step now is we want to replace those variable names with parameter values. And to do that, we define these strings. For example, S underscore V in is defined as 10. S underscore L is the inductance value, 62.5 E minus 6 microhenry, and so on. And we have marked some of these strings as to be changed by the user. So the user is actually going to find answers for the duty ratio as well as the resistance value, and then put those answers over here. That is the idea. Now we make a list of all of these strings, or to be more precise, these tuples, and that is given as an input to this function called replace strings 1. Let us see where this function is. So in our Jupyter GSEIM folder, there is a file called GSEIM calc for calculator. It's a Python file, and this file has a lot of useful functions, and the function that we just looked at, replace strings 1, is in this file. So let's open this file and search for replace strings, and that is the function here. And it is very similar to the code that we saw earlier. Essentially, it opens the input file for reading, opens the output file for writing, and for each line of the input file, it replaces the string such as $L with the value that the user has specified. When we execute this cell, all of these replacements are going to happen, and the original circuit file is now going to get replaced by this new circuit file. So let us execute this cell and see that it happens. Shift enter. Here is our Jupyter GSEIM folder, and here is the new file which has been created. And if we look at that file, notice that we don't see any $V in etc. anymore, but those have been replaced with the values that the user has specified. So we had $L here, now we have 62.5 E minus 6, and so on. Now that we have our modified circuit file with the appropriate parameter values, we can run GSEIM on that, and that is done by this system command, run GSEIM boost ccm7.in. If you are using Windows, then remember to uncomment this previous line. Alright, so let's execute this cell. So it has done that, and then there are a bunch of messages which we can ignore at this stage. It is basically telling us how many iterations it has taken and so on. Now this steady state waveform is actually an iterative procedure, and so what we are seeing here is the error or some kind of error at the beginning, which is like 12.9 here, and after the first iteration the error went to 19. After that it went to 7 10 raised to minus 5 and so on, and eventually it became very small, and that is where the steady state waveform computation converged and the program is completed. So the important thing to watch out for is this statement here, GSEIM program completed, and then this 0 here. If you see that, then that means the program has successfully completed, and now we can look at the data which has been created. In the next cell, we have Python code for computing average or RMS values, showing the output plots and so on. There's a lot of code here, and we are not going to go through all the lines here, but just point out what is done where. So this first part of the code essentially is used to get the data from the output files which have been generated. In this case, only one file. This part of the code is computing the average and RMS values for the various variables such as the inductor current, the switch current, etc. And here we print those values, and finally we have a matplotlib code which is used for plotting the various things. Let us execute this cell, shift plus enter, and now we see some of the things printed. It says average output voltage is 1.7 something 10 raised to 1, so it's like 18 volts. It is not what we wanted. We wanted 20 volts. So certainly the values that we have entered for the resistance and the duty ratio are not correct, and we'll have to go back and change those. In the meanwhile, let's also look at the plots, some of the plots. Here is the inductor current, and clearly this is not what we wanted. We wanted our converter to operate at the boundary between CCM and DCM, and this is clearly a case of DCM. We can also look at other variables such as the capacitor current, the diode current, the output voltage. Let us go back and change the resistance and duty ratio values, and that we do over here. So the resistance, the correct answer is 10 ohms here, and the duty cycle should be 0.5, 50%. So after making those changes, we execute this cell, run the solver by executing the next cell, and then run this cell with a lot of Python code which does all the calculations and plotting. And now the output voltage is nearly 20 volts as we wanted. Also the inductor current is at the boundary between DCM and CCM. So that's how the student or the user is expected to use this notebook and verify whether their answers are correct or not. This notebook was contributed by Professor Nakul Narayanan of Government Engineering College, Thrissur, and he could be contacted at this email address here. Alright, so that is all we have in this presentation, and I hope that you have found it useful, and I hope that you will find all these notebooks very useful for your teaching or learning, as the case may be.